Today we present our paper, Structured Query-Based Image Retrieval Using Scene Graphs, co-authored by Bridget Schroeder of the University of California, Santa Cruz, and Subarna Tripathi of Intel Labs. A structured query can capture the complexity of object interactions, such as woman rides motorcycle, unlike single objects, such as woman or motorcycle by themselves. Retrieval using structured queries, therefore, is much more useful than single object retrieval, but also a much more challenging problem. In this paper, we present a method which uses scene graph embeddings as the basis for an approach to image retrieval. We examine how visual relationships derived from scene graphs can be used as structured queries. The visual relationships are directed subgraphs of the scene graph with a subject and object as nodes connected by a predicate relationship. We propose to retrieve images from such queries and not from the RGB image features. In prior work, Johnson et al. Had a paper entitled Image Retrieval Using Scene Graphs, where a CRF-based model was used to match the best possible bounding box groundings from a query scene graph to a candidate image bank for retrieval. In another closely related work, Wang et al. Had a paper entitled Cross-Modal Scene Graph Matchings for Relationship-Aware Image Text Retrieval, where cross-modal scene graphs containing two modalities were used for image text retrieval. These relied upon both word embeddings and image features. We distinguish our work from these two previous works in that we do not use image features nor do we use word embeddings. The core idea in our paper is that we use subgraphs directly derived from scene graphs as queries for image retrieval. Each directed subgraph contains a subject and object node which is connected by an edge representing a predicate relationship. We use a similarity metric measured in Euclidean space for retrieval in a scene graph embedding space. The scene graph embedding is learned via a pretext task for layout prediction. An example of our image retrieval process can be seen on the left. A query, such as woman rides motorcycle, is converted into a query subgraph. That query subgraph is projected into a learned scene graph embedding space. We then query against a database using nearest neighbor search, where each image in the database has a corresponding subgraph which has also been projected into the scene graph embedding space. On the right, you can also see a corresponding image scene graph that corresponds to the image in the query database. We learn a scene graph embedding using layout prediction as a pretext task. We add two visual relationship-inspired losses as supervisory signals, namely a triplet superbox loss and a triplet mask loss to a layout prediction network. This is in addition to individual object mask and object localization losses. A visual relationship can also be thought of as a triplet of subject, predicate, and object embeddings. We pass these triplet embeddings to both the triplet superbox and triplet mask prediction networks. After the training of the layout prediction network, we use these triplet embeddings as the basis of our subgraph queries. In this slide, we're able to see the triplet mask prediction. Given a scene graph triplet, such as wall surrounding TV or keyboard below TV, we have corresponding image triplet patches in the ground truth image. From this, we are able to predict which pixels are subject in gray or object in white. The mask prediction is also used as a supervisory signal during training. Here we present qualitative image retrieval results for structured queries with object types of varying frequency in the CocoStuff dataset. We do not restrict the vocabulary of object classes which are used to form our queries, as was done in Johnson et al. We divide our classes into two types: head classes, which comprise the first 80% of objects in the CocoStuff dataset, and long-tail classes, which comprise the last 20%. In row A, we can see retrieval results for the highest frequency class, person, in CocoStuff. In rows B and C, we can see results for medium frequency classes, such as zebra or truck, and low frequency classes in row C, such as skateboard or skis. We measure image retrieval performance using recall at K as a metric. As a baseline, we break down our queries individually by subject, object, or predicate. We see that the contribution from the subject and object embedding is much more significant than the predicate, as seen in the figure on the left. Given the minimal contribution of the predicate, we examine structuring our queries with and without the predicate from the visual relationship, or triplet. We compare them using two types of models, those trained with and without triplet supervision. These are labeled as triplet or no triplet in the figure in the left. We see that the model trained with triplet supervision using a query structured with only the subject and object outperforms all model and query types by 10% in the best case. The triplet-based losses emphasize the interaction between subject, object, and predicate embeddings, and this may lend to the significant boost seen in the retrieval done with structured queries over the individual subject, predicate, or object embeddings. The figure on the right demonstrates the average retrieval performance on long-tail and head classes in the CocoStuff dataset. A low occurrence of an object class corresponds to a low occurrence of visual relationships with this object, making the task of image retrieval for long-tail classes more challenging. Despite this, the long-tail classes have a high recall at k, especially when k is less than or equal to 10. The results seen in this table summarize the results presented in the previous slide in the graphs. Again, we would like to emphasize that no input RGB image features were used during retrieval, and only the scene graph embedding features learned from the layout prediction model were used. The upper part of the table corresponds to the graph on the left in the previous slide. We see that adding a visual relationship inspired or triplet supervision loss boosts our recall by 10% in the best case. The bottom half of the table shows the performance of head classes versus long-tail classes. The table shows that long-tail classes tend to do at least as well as high-frequency head classes, or in some cases much better, especially at low values of k. We can see in the qualitative results slide in the previously that even the middle to low frequency long-tail classes have several matches in the top k equal 5 results. In conclusion, we have trained a layout prediction model in which a scene graph embedding is learned. We applied triplet-based loss functions which have been shown to greatly improve our image retrieval performance. We used structured queries formed from the learned scene graph embeddings instead of input image features for our retrieval. Finally, our approach achieves high recall even on the long-tailed object classes in the CocoStuff dataset. Thank you for watching our presentation, and please check out our paper online.